In general, the chemical and physical properties associated with main group elements display patterns of periodicity when arranged in order of increasing atomic number. Most of the elements on the periodic table are considered to be metals, and a metal is a substance that's characterized by its luster and its general ability to conduct both heat and electricity. Now, with the exception of mercury, metallic elements are all solids at room temperature. We define room temperature to be about 20 degrees centigrade or approximately 68 degrees Fahrenheit. Metals are also more or less malleable, and this means that they can be hammered into sheets for applications like car bodies, airplane wings, etc. Metals are also ductile, which means they can be drawn into wire for applications like running electrical wire through your house. Now, we've showed this many times before, but all of the elements to the left of this staircase on the periodic table display metallic properties. The one exception is hydrogen. Hydrogen is the first element on the periodic table and has its own unique properties, but the reality is it's a nonmetal, so it belongs over on this side of the periodic table. We place it above hydrogen just because of its electron configuration, but it does not react like a metal at all. Now, the nonmetals all lie to the right of that staircase. As you move down a column on the periodic table, the metallic character of elements increase. We define nonmetals as anything that doesn't exhibit properties of metals. Many nonmetals are gas. For example, chlorine and oxygen are both gas. Solid nonmetals tend to be hard, brittle substances with the exception of bromine, which is a liquid. Nonmetals tend to gain electrons during chemical reactions, and their donors tend to be metals. The elements that are bordering the staircase of the periodic table are called metalloids or semimetals. These are elements that have both metallic and non-metallic properties. These elements, such as silicon and germanium, usually make what we call good semiconductors. Semiconductors are materials that exhibit both conductive properties like copper, and they have the ability to act as an insulator like glass. Interestingly, the conductivity of semiconductors increases with increasing temperature. This is the exact opposite behavior of a metal. You've probably heard a lot about semiconductors because of their wide range of uses in electronics. The variations in metallic and nonmetallic properties associated with elements on the periodic table can be explained, at least in part, by the ionization energies of corresponding atoms. Elements that have low ionization energies tend to be metallic in nature, whereas elements that have higher ionization energies tend to be nonmetallic. Remember that ionization energy is the measure of a given atom's willingness to give up an electron during a chemical reaction. If ionization energy is periodic, then it shouldn't surprise you that metallic and non-metallic nature of elements is also periodic. Also, the basic and acidic nature associated with the oxides in a given group of elements form is actually a pretty good indicator of the metallic or non-metallic nature of that group of elements. We characterize oxides as either acidic or basic, depending on how they react with acids and bases. A basic oxide is one that will react with an acid, and an acidic oxide is one that will react with a base. Now, most Metals tend to form basic oxides, whereas most nonmetals tend to form acid oxides. An amphoteric oxide is one that will exhibit both basic and acidic properties. In this lesson, we plan to summarize main group elements' general electron configuration forms and metallic and nonmetallic behavior that is associated with each group. As well, we'll talk about their acid and base behaviors of the oxides they form. Now, elements that are in the same group generally do exhibit similar properties. However, the degree of similarity does vary depending on the group. For instance, group 1A, the alkali metals, do exhibit remarkable similarities, as do the elements in group 7A, the halogens. On the other hand, elements in group 4 tend to range from carbon at the top, which is a nonmetal, to lead at the bottom, which is a metal. We'll talk about hydrogen first. As we mentioned already, there really is no suitable group to place hydrogen in. It is the simplest element on the periodic table, since its atomic number is equal to 1. Therefore, its electron configuration is 1s1. Its single electron will go into the lowest possible energy shell. Now, hydrogen is usually placed in group 1A, but really it belongs in a category all by itself. Now, it is similar to the alkali metals in that it has a single electron in the s subshell, and it also forms H+ ions. However, hydrogen also forms H- ions when it is in compounds such as sodium hydride or calcium hydride. The most important compound that hydrogen can form is the one in which it forms during the combustion with air. When hydrogen is in the presence of air, it forms H2O, which is water. Group 1A is the alkali metals. These elements all have electron configurations in the form NS1. These are soft, very reactive metals, and their reactivity increases as you move down the column. In fact, these metals are so reactive that they are never found in pure form in nature. When these metals undergo reactions, they tend to lose one electron. They lose this single electron in their outer s subshell. Now, all of these metals react with water to produce hydrogen gas and a metal oxide compound. So let's look at the reaction between lithium and H2O. Lithium solid reacts with H2O to form lithium oxide and hydrogen gas. These metals will also react with air. When lithium is in the presence of air, but the primary component that is reacting with, of course, is O2, lithium solid reacts with O2 to form lithium oxide. Therefore, the oxides formed by the alkali metals will be in the form R2O, where R can be thought of as just any one of the alkali metals. So it could be lithium, it could be sodium, it could be potassium, etc. Group 2A consists of the alkaline earth metals. These elements have electron configurations in the form Ns2. This means that they've got 2 electrons in their outer s subshell. The alkaline metals are also chemically reactive, but they're not nearly as reactive as the alkali metals. The alkali metals are the most reactive metals on the periodic table. Now, like the alkali metals, reactivity increases as you go down this group of elements. Now, these elements also react with water to produce hydrogen gas and a metal oxide compound. For instance, barium solid, when in the presence of H2O, will form barium hydroxide and hydrogen gas. The alkali earth metals form oxides as well, but with varying degrees of reactivity. For instance, barium solid will react with O2 to form barium oxide. So the oxides that the alkaline earth metals form are in the general form RO, where again, R is just one of the alkaline earth metals. So it could be magnesium, it could be calcium, etc. Moving on to group 3A elements. This group of elements shows a slight increase in metallic character as you move down the column. And all of the elements have the electron configuration form Ns2 and P1, meaning their outer S subshell is completely filled, and they've got one electron in their outer P subshell. Now, the first element in the group is boron. Boron is considered to be a metalloid. The other elements in this group, aluminum, gallium, indium, and thallium, are all considered to be metals. Now, gallium is a pretty interesting metal. It has a very low melting point. In fact, gallium will melt in the palm of your hand. Boron is relatively unreactive towards oxygen, but the other metals will react with oxygen. For instance, aluminum will react with oxygen to form aluminum oxide. And the general oxide formula for this group of elements is R2O3, where of course again R can be either aluminum, gallium, indium, or thallium. The group 4A elements. Now this group of elements shows a dramatic increase in metallic nature as you move down the column. At the top of the column is carbon. Carbon, of course, is a non-metal, followed by two metalloids, silicon and germanium. And then we've got tin and lead, both of which, of course, are metals. Now, all of the elements in the group 4A have electron configurations in the form Ns2 and P2, meaning their outer S subshell is filled and they've got two electrons in their outer P subshell. The metallic elements in this group do not react with water, but they will react with acid. For instance, tin will combine with an acid, and then it will dissolve, form an electrolyte, and then hydrogen gas is released. Likewise, lead will also react with an acid. It will dissolve into the water, go into aqueous solution, and then hydrogen gas is also released. Now, group 4A, this group of elements forms oxides with the general formula RO2, where of course R can be carbon, silicon, germanium, lead, or tin. And the oxides progress from either being acidic to amphoteric, meaning they exhibit both acidic and basic properties. Carbon dioxide CO2 is an acidic oxide and it's also a gas. Silicon dioxide is also an acid oxide, but it exists as either quartz or white sand. Silicon dioxide is not a gas at all. It is very solid, a very solid crystal with an extremely high melting point. Germanium dioxide is also an acidic oxide, but slightly less than silicon dioxide. Now, tin dioxide and lead dioxide are both amphoteric oxides, and this should actually be SnO2, not Se. Moving on to group 5 elements. Now, this group of elements shows a distinct transition from nonmetal to metalloid to metal as you move down the column. They've all got electron configurations in the form Ns2 and P3, meaning their S subshell is filled, and they've got 3 electrons in their outer P subshells. The nonmetals in this group are nitrogen and phosphorus. The metalloids are arsenic and antimony. Antimony's elemental symbol is Sb. Then finally, the metal in the group is bismuth, Bi. Nitrogen occurs as an odorless, colorless, and relatively unreactive gas in the form N2. Nitrogen also makes up about 78% of the dry air we breathe on the planet Earth. White phosphorus, on the other hand, is a white waxy substance, and it has the form P4. Gray arsenic is a gray solid with a metallic luster. Antimony is a brittle solid with a silvery metallic luster. Then bismuth, the metal, is hard, lustrous, and has sort of a pinkish tint to it. Now, the metals in this group form various oxides in the form R2O3 and R2O5. Nitrogen forms many oxides, actually: NO, NO2, N2O4, and N2O5, all of which are gas with the exception of N2O5. Phosphorus forms 2 acidic oxides in the form P4O6 and P4O10. Arsenic forms 2 acidic oxides, ASO3 and ASO5. Antimony also forms SbO3, Sb2O5. And lastly, the metal of the group forms Bi2O3. Moving on to group 6. This group of elements is called the chalcogens. And these also show a transition from nonmetal, being oxygen and sulfur, and also selenium, to metalloid, tellurium, then lastly to metal, polonium. They all have electron configurations in the form Ns2 and P4, meaning their outer S subshell is filled with 2 electrons, and they've got 4 electrons in their outer P subshell. Oxygen, like nitrogen, is an odorless gas, generally in the form O2. Oxygen makes up about 21% of the air we breathe. Sulfur is a brittle yellow solid with the form S8. Tellurium is a shiny gray, brittle solid and polonium is a silvery metal. Now, sulfur, selenium, and tellurium all form oxides in the form RO2 or RO3. Group 7A. Group 7A is called the halogens. Now, we said the alkali metals were the most reactive metals. Well, the group 7A elements, the halogens, are the most reactive nonmetals. The general formula for halogens are in the form X2, where X symbolizes the halogen. It can be fluorine, chlorine, bromine, or iodine. Fluorine, F2, is a pale yellow gas. Chlorine, Cl2, is a pale greenish yellow gas. Bromine, Br2, is a brownish yellow liquid, and iodine, I2, is a bluish black solid, and it also has a violet vapor. Now, not much is known about astatine, atomic symbol At, because all of its isotopes are radioactive and they have very short half-lives. We'll talk more about half-lives when we talk about nuclear chemistry, but a half-life is the time it takes for half the isotope to decay or break down into another element. The halogens all have electron configurations in the form Ns2, Np5. And this is very important because they have a very large desire to fill their outer p subshell. It only needs one electron to be completely filled. Once they fill this outer p subshell, they'll have an electron configuration identical to the noble gas element at the end of their respective period. Now, each halogens tend to form many oxides and generally are very unstable acidic oxides. Group 8A is the group of elements that are known as the noble gas elements. All of these elements have an electron configuration in the form Ns2, Np6. Notice that their S and P subshells are both completely filled. These elements are nearly unreactive due to the stability of their electron configurations. Both their S and P outer subshells are completely filled. For a long time, these elements were thought to be completely unreactive until in the 1960s, several xenon compounds were prepared. And now compounds with krypton and radon are also known. There are no compounds that I know of that have been created with helium, though. Helium is the noble gas element at the very top. Its electron configuration is 1s2 because it has 2 electrons. To conclude, in this lesson we investigated chemical and physical properties that are associated with main group elements. These variations of metallic and nonmetallic properties can be explained in part by the ionization energies of the corresponding atoms. Elements that have low ionization energies tend to be metallic in nature, whereas elements with higher ionization energies tend to be nonmetallic in nature. Elements that are in the same group generally do exhibit similar properties. However, the degree of similarity does vary depending on the group. For instance, group 1A, the alkali metals, do exhibit remarkable similarities, as do elements in group 7A, the halogens. On the other hand, group 4A elements tend to range from carbon at the top to lead, which is a metal, at the bottom.